All right. So we are back. We're going to be taking a look at some more sophisticated influence forces. This is for if you have a specific case, if you're, like doing tornadoes, if you're doing magic, you're going to be creating something like this for sure to direct your forces to your will. All right, so let's take a look at how this was made. We create a curve. We're going to resample it. So we have that curve view attribute. By now, you know the curve view is going to do a 0 to 1 mask along our curve. We do an orient along curve. This will give us a vector field flowing along the curve. In this case, I'm putting it into the normal, but you can put it into, even put it to velocity. There you go. It's a better way to visualize it. That's how it's going to look like. It's going to be flowing along the curve. And then I just put it upwards. I create a empty VDB field, call it vel, and put it to a vector float. And then I just activate it by this bounce. So you do a bounce, it's going to do a box for you based on the curve. And then you VDB activate by reference, and it's going to give you an empty field that has voxels, and it's a vector, and it has a velocity field in it. So now we can do a bunch of things with it. So all of this, which I will do from scratch because it's going to be easier to explain, but it looks like this. So it's just a field that's flowing upwards, and a better way to visualize it is like this. Even a better way to visualize it is with some particles. So if you do a popnet, you will be able to see how your force will flow. And I like this one. It has a very fluid-like motion to it. I even did another one here a few seconds before. And this one had an even more fluid feel to it, which I like quite a lot. So again, magic, fluids, whatever you want. This can give you a good start with these types of effects. Okay, I'll disconnect this. So how does this work? Let's do a volume pop. So we plug in our empty velocity field and our curve. We're going to be using the curve data that we created, especially the tangent here, to create some more vector fields. So let's create the first one. And let's do a PC open. This is going to look up at our curve data based on the search radius and the number of points. We need a point cloud filter, and let's use the position for now. So this will look up the position on our points here on this point cloud. It's a cloud made out of points. And it's going to look at the voxel position that we have in this box. Let's also bind export our velocity back. Call it vel. So let's create an actual vector field now. We're going to subtract our voxel position and our point position, and let's see what we get. The best way to visualize things like this is to scatter points on your volume. By the way, here I'm creating the same setup, but instead of doing a velocity field, I'm creating that influence field that we all know we need. for the Axiom influence fields to work. And I'm referencing that as well, and then just scattering points to it. So now with a volume trail, we will be able to see what we get here. So let's go inside and increase the search radius. So now our curve points are here, and it's taking, we're subtracting from basically the voxel position data and our point position data, and this is the vector field that we're getting. Pretty cool. What else can we do with this? So let's create another PC open and bring in that normal field that is the tangent. So just normal, still a vector field, and let's plug in here. So we get this flow of our curve, and you can control the radius with this, but that will give us a direct flow of our curve. And sure, if you plug that in to your particles, they're going to flow directly alongside the curve. So for a lot of cases, maybe that's exactly what you need. So you can stop right here. But if you want to add more controllability to it, we can continue. So we have this. What we can do now is we can do a cross product between this vector and this vector, and that will give us a rotation force, which is pretty cool. What we can do now is mix between the two, between the rotation force and just the up. So we are now mixing between full rotation and no rotation. And if you do just a bit, you're going to start getting some nice rotation happening here. We can now also mix between this rotation with the cross product and the suction force. So now we are either the suction force is taking over, or we can release some of the up motion and the rotation motion. So now you can see, even just with this, you can start sculpting and getting some really awesome velocities. Maybe let's increase our search radius. So you can see our velocities now are nicely bending to the curve. And this is not, just exclusive to this curve. What you can do is you can either duplicate the curve, you can maybe add another one, right? So, oops. It's not going to be maybe the best example, but it is going to work. So you can do, oh yeah. So one is like that. Sure, why not? But you can see by adding multiple curves, it's still going to work. It's just going to be sampling the other curve in as well. Right. Let me go back to just a single curve. You can also use different shapes. It doesn't have to be a curve. You can use a sphere, a circle, or whatever. Whatever you want. That's what I'm trying to say. So you have this. Let's continue. We have that curve U attribute here. So we can bring that to the mix as well. And this one is a float field. Let's put it through a ramp. And let's just see if we do, look at this one, actually this suction force. Let's just do another mix. So we have this and the suction force. Yeah, that's fine. I'll do it on here. So in this mix, we can now plug in into the bias our ramp, and this ramp now will control how much up movement or the rotation we have. So we're mixing between full rotation or the up movement. And if you use this bias, you can see in the beginning everything will be moving up super fast, and then it's gonna go into the rotation. So you can also fit this range if you want to here to get more control. So that's how you can use the bias. We're not going to use it for now. Just use the basic bias mixing here. And another thing we can add is some curl noise. So let's see what that will do. And this is just to spice things up. Curl noise, it's just gonna curl everything. Let's make it a bit bigger. And you can see now it's curling everything, but we kind of want to control that a bit. So we do have this subtract here, which creates a vector field. But we do need we kind of need a mask. And to create that mask, we need to calculate the length of this subtract vector. And now we can plug that into the amplitude. And you can see this is kind of how our mask looks like. And we can fit it. I think it was 5. And if you invert this, you will see we can subtract and just add the curl noise just to the center of this effect. So now, let's see if we add we can now add some curl noise here. Just trying to tidy things up a bit. Add it here. And what we can also do is a multiply constant to get more of it. So you can see if we multiply it by a lot, we get the velocity fields happening on the inside. And if we expand this, let's go back to 1. We start expanding, you can see how that is going to affect our velocities. And you can try adding it in different places to get a different type of result. But you can see now we have some vector fields, curl noise happening, but it's only happening on the inside, and it's neglecting all the areas outside because we are using this length as a mask. Cool, so we have most of our things in place now. And the second best way to visualize this is if you just create a circle, scatter some points below, you will actually see the growth as it would occur. So that would be the difference between this and this. So let's plug it in. And you can see that this is exactly how our velocity is going to flow. So if we plug this into our popnet, that's how our velocity is going to behave, which this is a bit, not exactly accurate in terms of how our velocities are going to flow. So I find that this is a good way to actually visualize it. And the only other thing is you need your trail length to be a bit longer. But you can see it's actually going to represent how your velocities are going to work in the simulation. So with this in mind, we can now go back inside and start changing some values here. So I like the amount of the rotation, but this mix is probably way too strong. So remember, this is mixing between the rotation and yeah, so now it's going to be difficult to see with that other visualizer. And maybe let's remove some of the curl noise. Yeah, very good. And now this is how this will look like. Pretty neat. Inside of here, I'm just using a pop vec by volumes. You put it to update velocity and then some pop force and a basic pop drag. Nothing special. So now that we have these volumes, I'll just use the other ones as because I already have them. They look like this. The one we just made looks like this, so it's fine. You have this, you rename it to influence vel, as we know from the previous lessons. This is we're exporting vel, but let's rename it to influence vel. And we need our influence that we're creating here. We merge them together, so we have both of them. And then in the Axiom solver, it's, yeah, you're gonna get this. So you can visualize it with the velocity trail. This is how your velocities are gonna be flowing. Now I'm using a pull here, so this is something that we haven't used yet. So pull will try to match this velocity field to the speed of this velocity field. If we add this to add, it's just going to be adding those velocities each frame step, and it's going to go crazy because essentially it's going to look at these velocities here, and it's going to start pushing everything in this direction. But then by this point, this velocity is so high that our velocities of the curve that should be going left are not going to be enough. So our smoke is just going to go crazy, and then it's going to come here, and you can see it's going to start using some of the swirliness, and it's just going to be a mess. You can use this to a certain degree if you go super low with your velocities. It's kind of going to respect the flow, as you can see, because it's not going too crazy, but it's still going to go outside the bounds. So the best way here is you either replace the velocity, which means that it's going to completely take the velocities that we're feeding it, which gives a nice effect as well. In this case, you would have to animate some values here. So, you know, if we would be animating the offset, for instance, just do $F in all of them. We'll get a more natural feeling now, and that is because our velocities are actually, you know, moving. Our curl noise in this example is actually moving. Or you put this, just disable the offset, you put it into pull mode, and now you can control the acceleration that's happening. So you can say, no, match the speed very fast. Or you can say, well, just do kind of an in-between, which usually works the best. And we can start adding some turbulence. Let's go crazy. So you can see we have our turbulence affecting plus the velocity. And then you can go, you know, crazy and start animating the curve. And if you animate the curve left and right with some bending, your effect will change based on that as well. And that's how you can get very controlled velocity fields. All right, so let's take a look at this simple vortex animation. This is also good for magical effects or, you know, portal effects or whatever you want. Let's take a look at how this was done. Also quite simple. Just creating some vector fields using a cross product and normalized position. So keep in mind, because I'm using position here. Oh, this is pretty cool. This will only work if you are in the center, because we're using the outwards position in this case. So back to the center. rasterizing density, scattering points inside, copying back the velocity fields. PopNet, very simple. There's nothing inside the PopNet except this pop force. Everything else is driven by that velocity field. And I'm changing the global seed, so it feels like, oops, it feels like the points are spawning in different places all the time. Removing all the attributes, we only need the position and velocity. And then I'm using the spiral source, which is quite handy to create the necessary data for us. So the pyro source will create density, p-scale, and velocity data on the points. This scale is pretty much the p-scale that we were setting in the fire examples. And then you rasterize them. On the left side, we have just density and vel, which is what Axiom will need to spawn things. And then on the right side, we have the influence fields. So I'm just splitting them between density and V. And as you know by now, we need to rename it to influence and influence vel, merge everything, merge it again, and we will get some swirly smoke goodness happening. It's always good to follow my own rule of file caching the emitter. There we go. Very cool. All right. Another way of doing this, if you don't want to use this workflow with these two guys, you can just do VDB from particles and it will pretty much do the same thing. And here you can just say density and vel, right? Even V will work, but let's use the right naming conventions. Now in this case, we're not inputting the influence, so it's purely driven just on the basic velocity field, which is this guy, instead of the influence fields. But you can see it's going to work pretty much in a similar fashion. And then here on the left, we have a pretty much similar effect, just particles going downwards. The only difference, what I'm doing here, is that I'm using this volume rasterized particles, which will give me the velocity blur already on the volumes. So you can check this example as well. But yeah, that's it when it comes to our custom velocity forces and controllability with influence fields.